Hey guys, I'm sorry it's been so long since I've posted. This has been an insanely busy week. I finally finished moving into my new house, and so, this is just the first opportunity I've had to post a video since the last time I talked to you guys. Um, we have a lot to cover today, so I'm going to be trying to cover it pretty quickly. And once I've covered it, as promised, I'm going to give you guys some homework problems to work on. And over the course of the next couple of videos, I will be giving solutions to some of those problems as they are related to, the next several topics that we discuss. So, to start out with, I wanted to remind you of the inference rules that we have so far. So remember, we have 5 different logical connectives: not, or, and, if then, and if and only if. And for each logical connective, we're going to have one introduction rule and one elimination rule. And so far I have given you introduction and elimination rules for or and for and. So the introduction rule for or tells us that if you have the premise P, that proves P or Q. It also proves Q or P. And the elimination rule tells us that if we have two premises, P or Q, and not P, those two premises prove Q. For and, our introduction rule says that when we have two premises, P and Q, those premises prove the conjunction P and Q. And the elimination rule just tells us that when our premise is the conjunction P and Q, that proves P or it proves Q. All right. Now, one of you asked in a comment on the last video what the difference is between entailment and proof. We only use prove, the singleton style, when we can show that an argument is valid by using our inference rules. We use entails, the double turn style, whenever an argument is valid, whether our inference rules allow us to prove it or not. Okay, right now, for example, I have only given you guys 4 inference rules, and there are a lot of valid arguments that using those rules, there is simply no way to prove. I'll give you an example of one in a minute. But when you're looking at an argument like that, when you're looking at an argument that cannot be proven with the inference rules available to you, it's still appropriate to use entails to describe the relationship between the premises and the conclusion. It is not appropriate to use proves, because to say that the premises prove the conclusion is to say that there is a way of deriving the conclusion from the premises using nothing but the inference rules you have. Okay, so here is an example of a valid argument that you cannot prove with the 4 inference rules that you have so far. There's just one premise. Here's what it says. It's just not true that I am not handsome. And your conclusion is, therefore, I'm handsome. All right, now, the premise here is not a conjunction. It is not a disjunction. And the conclusion is also not a conjunction or a disjunction. And so, none of the inference rules you have are going to give you any way at all to get from the premise to the conclusion. So if you only use the inference rules I've given you so far, this cannot be proven. Okay, you cannot prove the conclusion from the premise using the inference rules you have. But the premise does entail the conclusion. This is a valid argument. And to see why, just pretend that the conclusion is false. If the conclusion is false, I'm not handsome. And now look at the premise. The premise says that's not true. So if the conclusion is false, the premise has to be false. That means this is a valid argument. Okay? And this argument is actually going to be our example for the next inference rule I give you. Okay, so let H be the statement I am handsome. Then here's what this argument says. Your premise is not H. It is not the case that I am not handsome, and that entails H. Okay, now as always, it doesn't matter what our statement variables stand for. It doesn't matter what statement variables we use. And so in general, not P entails P. And we're just going to be using that argument as our, not elimination rule. Our rule says not P proves that P. All right? Now, a statement that begins with the not sign is called a negation. A statement that begins with two not signs is called a double negation. All right, so our not elimination rule says that a double negation entails the statement that is double negated. I'm not going to give you our not introduction rule yet, because it's pretty complicated. It's a lot more complicated than any of the rules that I've given you so far. So before I give you the not introduction rule, I'm actually going to give you the conditional elimination rule. All right? Here's an example. I've shown you this argument before. This argument is valid. If you want to understand why it's valid, you can go back and watch one of the previous videos. But you have two premises here. The first premise says, if the street is white, it's snowing. The second premise says, the street is white. And the conclusion is, so it's snowing. All right, now, if we let W equal the street is white and S equal it's snowing, then this argument has two premises, W arrow S and W, and those two premises entail S. Now, as always, as I say every time we have a new inference rule, it doesn't matter what our statement variables are or what they stand for. And so in general, the premises P arrow Q and P entail that Q. And that's going to be our arrow elimination rule. So our arrow elimination rule says P arrow Q and P prove that Q. All right. Now, a statement of the form P arrow Q, a statement that you symbolize with an arrow, an if-then statement, is called a conditional. Okay? P is the antecedent of the conditional P arrow Q, and Q is the consequent of that conditional. All right, now, there are a lot of different English words and phrases that are often best symbolized using conditionals. All right? If you look on the screen now, you can see a whole list of them. So the statement, if P then Q, that's symbolized P arrow Q. If someone says P only if Q, that is also symbolized P arrow Q. Okay, be careful with this one, because if someone says only if Q, then P, that's P arrow Q. Okay, the arrow points toward the letter that comes after the only if. All right. If someone says P is sufficient for Q, again, that's very often best symbolized as P arrow Q. But if someone says P is necessary for Q, that's usually best symbolized as Q arrow P. All right. P unless Q is usually symbolized not Q, arrow P. So if you think about this one for a second, it makes a lot of sense, right? If your mother says, I will punish you unless you do your homework, what that means is if you don't do your homework, then I will punish you, right? So P unless Q is not Q, arrow P. And if someone says P is not true without Q, that is usually best symbolized not Q, arrow not P. All right. You have to be very, very careful, though, when people put negations in front of conditionals. Sometimes this is not symbolized the way you might think. So if I tell you it is not the case that if P then Q, the best way to symbolize that is almost always P arrow not Q. All right, the best way to symbolize that is not P arrow Q. Okay, that's completely wrong. It is not the case that if P then Q is symbolized P arrow not Q. All right, this is going to be important, and I'm going to bring it up again later in today's video. All right, so now we have 6 inference rules. Here they all are. I've given you elimination rules for not and for if then. Okay? I still have to give you the introduction rules for both of those symbols. And like I said before, this is a little bit complicated, but I'm going to try to explain these ones for you right now. So we're going to start with the not introduction rule. And here's a story I want you to think about to help you understand the rule. Imagine that Jackie is at church one day, and the preacher tells her that God knows everything, is perfectly good, and is able to do whatever he wishes. And so the preacher says that Jackie should listen to God. Why? Well, because there's so much evil in the world, and God will help protect her from it. And Jackie says to the preacher, "Preacher, that means God does not exist." So the preacher is shocked. The preacher says, "Why?" "Well," says Jackie, "let's pretend that God exists. Since he can do whatever he wishes, he can prevent all the evil he knows about if he wants to. Since he knows everything, he knows about all evil, and since he's perfectly good, he'll want to prevent as much evil as he can. So that means God must prevent all evil. But you, preacher, said there's evil in the world. So supposing God exists, all evil is prevented, even though there is evil. And that makes no sense. It makes no sense. So the only logical conclusion is that God does not exist at all." All right, now, I do not want you to think about whether all of the premises of this argument are true. What I want you to think about is the logical structure of what Jackie says here, all right? And it really comes in like 4 different steps. Jackie wants to prove a negation, okay, not P. She wants to prove that God does not exist. And so she begins by supposing, or by pretending, the opposite of what she wants to prove. Okay, she supposes that God does exist. And she uses that statement, combined with all of the other premises that the preacher had given her, to prove something that is contradictory. To prove that evil is all prevented, but that evil still exists in the world. Okay? Now remember, we talked last time about how contradictions cannot be true. Statements of the form Q and not Q, or P and not P, cannot be true. And so a supposition that entails a contradiction also cannot be true, right? That's what entails means. Entails means that the premises cannot be true unless the conclusion is true. Since a contradiction can never be true, no statement that entails a contradiction could ever be true. So, given that the rest of the premises in the argument are true, P must be false because it allowed us to prove a contradiction. And that means that not P must be true. Okay? That's the idea that Jackie has. She supposes the opposite of what she wants to prove, and then she shows that that supposition led to a contradiction. Okay, it led to a conclusion that could not possibly be true, and that means that the supposition must have been false. Okay. In general, let gamma be the set of premises in an argument, and let P be the opposite of the negation that you are trying to prove. Here is the inference rule. If gamma plus P proves Q and not Q, then gamma proves that not P. Okay? I'll give you an example of how to use this in just a minute. But before I do that, I want to explain a little bit more precisely why this is a good rule. Here's the explanation. Remember that to say that an argument is valid is not to say that the premises are true. Okay? Valid means that the conclusion cannot be false if the premises are true. Okay? Now, a statement like Q and not Q cannot possibly be true. And that means that gamma, no matter what it is, does not entail Q and not Q unless the premises in gamma cannot possibly be true. In other words, if gamma entails Q and not Q, then gamma contradicts itself. And like we talked about last time, self-contradictory statements can be used to prove literally anything. So if gamma contradicts itself, then one of the things that gamma entails is not P, because gamma entails everything. So that's what happens if gamma is self-contradictory. Now suppose that gamma is not self-contradictory, but that when you combine gamma with P, that entails Q and not Q. Well, since Q and not Q can't possibly be true, P has to contradict gamma. And that means that P is not true unless some statement in gamma is false, namely the statement that P contradicts. Well, here's what that means. That means not P is not false unless some statement in gamma is false. And that's just the definition of validity. That's the definition of saying that gamma entails not P. So, if gamma combined with P entails Q and not Q, there's only two options. Either gamma is self-contradictory, or P contradicts gamma. And either way, gamma entails not P. All right, so this is a good inference rule. If gamma combined with P proves Q and not Q, what that means is that gamma proves not P. Okay. Here's a very, very easy, useful argument that we can prove using this inference rule. All right, P arrow Q, not Q, proves not P. All right. Here's how you prove this. Our first premise, line 1 of the proof, says P arrow Q. The second line of the proof says not Q. All right, that's the second premise in the argument. And now notice that I've indented line 3. I've moved line 3 to the right. Okay. The reason I've done this is that 3 is something that we are just supposing to be true. It's not something that we've proven. It's not a premise. We're just going to pretend for a moment that it's true. Okay? And now, everything else that we use statement 3 to prove, we're also going to indent. We're going to keep it lined up under statement 3 to remind us that it's not really something we've proven. It's just something that would be true, supposing that statement 3 were true. All right? So statement 3 is a supposition. Now look at line 4. Line 4 just says Q. That comes from line 1 and line 3 using our arrow elimination rule. Okay. And now look at line 5. Line 5 says Q and not Q. Now, that comes from line 4 and line 2, right? 4 says Q, 2 says not Q. So using our and introduction rule, we get a contradiction, Q and not Q. All right, now look what happened. Gamma is just our premises. It's lines 1 and 2. And we've combined gamma with a statement on line 3. And that combination of statements proved a contradiction on line 5. What does that mean? It means our original premises prove the negation of the supposition on line 3. All right, so line 6 is not indented anymore. It's not lined up with statement 3. It's lined up with statements 1 and 2. Okay, and what we read on line 6 is just not P. Okay, that comes from lines 3 through 5 using our not introduction rule. And that's what we were trying to prove. All right, so that proof is finished. I'll give you another example later on in this class of how to use this rule, and then I'll give you a lot of problems to practice with. So you should get used to this pretty quick, but that's the basic idea. So now you have 7 rules. Here they all are. Okay, if you look at our not introduction rule, it says if gamma plus P proves Q and not Q, then gamma proves not P. Okay. Now, the arrow introduction rule is a lot like the not introduction rule. Okay. Here's what it says. If gamma is a set of premises, okay, then whenever gamma plus P proves that Q, gamma proves if P then Q. All right. Here's what I mean when I say this is similar to the not introduction rule. This rule, like the not introduction rule, requires you to suppose that something were true, and then see what you would be able to prove if it were true. Okay? So if you just suppose that P is true, and that supposition allows you to prove Q, what that means is that if P were true, Q would be true. In other words, P arrow Q. That's the idea. All right? So here's a more detailed way of convincing yourself that this is a good rule. Suppose that gamma proves that Q by itself, without any supposition at all. If that's true, then gamma definitely proves P arrow Q. Why? Well, because if-then statements are weaker than their consequence. Okay? If you've proven the consequent of an if-then statement, you've already proven something much stronger than the conditional. For example, if I can prove that 2 plus 2 equals 4, then I don't need to prove 2 plus 2 equals 4 if it's raining, right? Since I've already proven that 2 plus 2 equals 4, that means it's true no matter what conditions there are. All right? And so if gamma proves Q, then gamma proves P arrow Q. All right? Now, suppose that gamma doesn't prove Q, but that gamma combined with P does prove Q. Well, what would that mean? It would mean that even though gamma does not prove Q, gamma would prove Q if P were one of the premises. In other words, assuming that the premises are true, if P were also true, Q would be true. In other words, gamma proves P arrow Q. All right, so if gamma plus p proves q, there's two different options. Either gamma proves q all by itself, or gamma does not prove q, but it would prove q if p were added. Either way, gamma proves p arrow q. All right, so this is a good inference rule, and I'm going to give you an example of an argument that you can prove using this inference rule. Using this inference rule, just to kind of give you an idea again of how this works. All right, so here's the argument. Your premises are p arrow q and q arrow r, and we're going to use that to prove p arrow r. All right, so just to give you an idea of what this says, if something is a dog, it's an animal. If something is an animal, it's a life form. So if something is a dog, it's a life form. All right, something like that. How can we prove this? Well, statement 1 is your first premise, p arrow q. Line 2 of the proof is your second premise, q arrow r. And now, what we want to prove is a conditional. We want to prove p arrow r. So we're going to use our arrow introduction rule. And to use that rule, we start out just supposing that the antecedent of the conclusion that we're trying to prove is true, right? We're just going to suppose that p were true. That's line 3. And just like before, I've moved line 3 to the right to remind you that this isn't something that's really true. It's just something that we're supposing is true. All right. So line 3 says p. That's a supposition. And now line 4 says q. That comes from line 1 and line 3 using our arrow elimination rule. Line 5 says r. That comes from line 2 and line 4 using our arrow elimination rule. And that's just exactly what we wanted, right? We supposed that p was true. And using that supposition, we have been able to prove that r would be true. Okay? That means that our premises prove p arrow r. So line 6 just says p arrow r. And again, that's lined up with statements 1 and 2. It's not lined up with statement 3. Because, line 6 is not something that we only proved supposing that statement 3 were true. It's something that we've proved just using our premises. And we've proven it with lines 3 through 5 using our arrow introduction rule. All right, now, again, I'm going to give you an example later on in the video that is going to use this rule again, just to sort of, give you one more example of how it works. But that's 8 inference rules now that you have, right? So if you look at the chart on the screen, I've added the arrow introduction rule. Here's what it says. If gamma plus p proves that q, then gamma proves that p arrow q. Okay. Now, the only logical connective we have left is if and only if, the arrow that points both directions. All right. And all you need to know about this symbol is that p double arrow q is just a convenient way of writing p arrow q and q arrow p. And so the inference rules for if and only if are really just identical to the inference rules that we use for and. Okay? The introduction rule says that if your premises are p arrow q and q arrow p, those premises prove p if and only if q. And the elimination rule says that if your premise is p if and only if q, that premise proves p arrow q, and it proves q arrow p. Okay, so it's just like and introduction and elimination. Okay, a statement of the form p if and only if q is called a biconditional. All right, and so with that, that's all 10 of our inference rules. And And those are all of the inference rules that I am going to be giving you for a long time. These inference rules are enough to prove all sorts of different things, and we're going to have a lot of examples of things that you're able to do with just these rules before I start introducing you to some topics that are a little bit more complex. All right, now, before I give you some homework problems to work on, some proofs to do on your own, I need to give you two more important symbols. Okay, here they are. The first one looks like 4 dots, and that symbol means is logically equivalent to. All right, so we say P is logically equivalent to Q if and only if P entails Q and Q entails P. All right, so if you see P, then 4 dots, then Q, what it means is that P entails Q and Q entails P. Okay, so if you want to prove that P is logically equivalent to that P is logically equivalent to Q, the way you do this is you have one proof where you have one premise, P, and your conclusion is Q, and then you do a second proof that has one premise, Q, and the conclusion is P. All right, here's your second symbol. It looks like kind of like a 0 with a slash through it. This is the empty set. All right, the empty set is what we use to refer to a set of premises when there are no premises at all. All right, so if I write the empty set proves P, what that means is that it's actually possible to prove that P is true, even if you don't use any premises at all. Okay, in other words, to say the empty set proves P is to say that P is true no matter what. All right? Now, knowing those symbols, I'm going to put 2 slides up on the board that are just nothing but homework problems. Here's the first one. All right, and you can see that all of these arguments on the board, they say that different statements are logically equivalent to each other. All right, to prove the 2 statements are logically equivalent, again, you use the first one to prove the second one, and then you use the second one to prove the first one. And if you look at the first argument on this screen, it actually says that 3 different statements are all logically equivalent to each other. All right. Here's the second set of problems. You'll see that 3 of these say that the empty set entails something. And so what that means is that you have to prove the statement on the right without using any premises at all. If you think for a minute about how to do that, you'll realize that you have to use the not introduction rule, all right? Or the arrow introduction rule, one or the other. If you use either of those 2 rules, remember those rules allow you to prove things only using suppositions, all right? And so those 3 problems, you're going to have to use either the not introduction rule or the arrow introduction rule in order to prove them. All right, now some of these questions are pretty difficult. Some of them are pretty easy. I'll be going over solutions to many of them in my next couple of videos. All right, before I go, I just want to give you one more kind of a practice argument. This is one of my favorite arguments. I think it's really fun. This argument is an excellent example of what can go wrong if you make a mistake in the way that you symbolize an argument. So here's the argument. 2 premises. The first premise says, if God does not exist, it is not the case that if I pray, then God answers my prayer. The second premise says, I do not pray, And the conclusion is, therefore God exists. All right, now, the first premise of this argument is obviously true, right? If there's no God, then he does not answer prayers. All right. The second premise is also true. I don't pray. All right. But the argument is obviously invalid, right? The fact that I do not pray does not prove that God exists. But if you symbolize the first statement incorrectly, then all of a sudden you end up with a valid argument. So I'm going to show you the wrong way of symbolizing this argument, and I'm going to use it to prove that God exists. And I want you to think about what I've done wrong in the way I've symbolized the argument. All right, so we're going to let G mean God exists. We're going to let P mean I pray. And we're going to let A mean God answers my prayer. So look at line 1 of this proof now. It says, if God does not exist, then it's not the case that if I pray, then God answers me. Okay? And that's a premise. That's the first premise of the argument. Line 2 is the second premise. It says, I do not pray. All right? Now, what I'm trying to prove is that God exists. And I don't see any obvious way of doing that. And so I'm just going to try to use my not introduction rule. I do this a lot. When I don't know how to prove the conclusion that I'm looking for, I assume the opposite, right? So I'm just going to suppose that God does not exist. And then I'm going to try to find a contradiction. So, line 3, I've moved it to the right because it's just a supposition. And what I'm supposing is that God does not exist. Now look at line 4. Line 4 comes from line 1 and from line 3 using my arrow elimination rule. So it is not the case that if I pray, then God answers me. And now remember, what I'm trying to do is I'm trying to find a contradiction. And so I would like to be able to prove something that contradicts line 4. In other words, I would like to be able to prove P arrow A. All right? The only way to prove a conditional is to use my arrow introduction rule. And to use that rule, I have to suppose that the antecedent of the conditional is true. So on line 5, I'm going to make another supposition. I'm going to suppose that P. And I've moved this even further to the right? Because P isn't something that's true, it's just something that I'm supposing. And I'm only supposing it because I've already made another supposition on line 3. Okay? So, line 5, I suppose P, and what I'm trying to prove is A, and I don't see any obvious way of doing that, and so I'm going to make another supposition. I'm going to suppose that A is false. So line 6, I move it even further to the right. I suppose that not A. And now if you look, I have a contradiction. Line 5 contradicts line 2. And so on line 7, I write P and not P. That comes from line 5 and line 2 using my and introduction rule. And so on line 6, I supposed that A was not true. And on line 7, I got a contradiction. So line 8, I conclude that the supposition from line 6 was false. So line 8 says not A. Okay? That comes from line 6 through 7 using my not introduction rule. And remember, line 8 does not get lined up with line 6. Line 8 is not something that I have only proven supposing that not A is true. Line 8 is something that I've proven just supposing that P is true. So line 8 gets lined up with line 5. All right? Line 9 just says A. That comes from line 8 using my not elimination rule. And A is what I was trying to prove when I made the supposition on line 5. So line 10 says P arrow A. If P, then A. Okay, that comes from line 5 through 9 using arrow introduction. Okay, and again, this is lined up with line 4, not with line 5. Why? Well, because P arrow A isn't only true if the supposition on line 5 is true, right? The supposition on line 5 allowed me to prove the statement on line 9. In other words, supposing P allowed me to prove that A. And so P arrow A is true, even not using the supposition on line 5, okay? So line 10, you'll notice, contradicts line 4. And so on 11, I write down P arrow A and not P arrow A. That comes from line 10 and line 4 using and introduction. And now look at what that means. I made a supposition on line 3. The supposition on line 3 led to a contradiction. So that supposition must be false. So line 12, which is now lined up again with my original premises, says not G. That comes from line 3 through line 11 using my not introduction rule. And now line 13 just says G using my not elimination rule. All right, so the way that I symbolized this argument, it's valid. My premises really do prove the conclusion. All right, now figure out what's gone wrong. Okay, I've told you I've symbolized one of the premises incorrectly. I want you to think about what's wrong with the way I've symbolized it and why, and I'll talk about this more in my next video, and also go over, some of the other problems that I gave you guys to work on. All right, good. I'll see you next time.